What's up, party people? My name is David G, and I'm going to be demonstrating magnification using crappy shadow puppets. To help me do this, I have my lovely assistant, Maddie G. Say hello to the people.
Hello, people.
All right, you want to say anything else?
Give my dad an A in this project.
All right, we're going to do this. Magnification!
So what we have here is your basic headlamp. It represents the X-ray tube where the X-rays are coming from. Maddie G has a bunny that we'll be imaging today. In this example, the source to image receptor distance is very short. The shadow being casted onto the image receptor will be our image. As you can see, the image will be very magnified with this source to image receptor distance. Here, I've increased the distance a small amount. Despite my crappy aim, you can tell the shadow being casted is smaller, therefore giving us a less magnified image. In this example, Maddie G's butterfly is not on the image receptor, creating an increased object to image receptor distance. As you can see, the shadow, or the image, will be extremely magnified. To compensate for this, decrease object to image receptor distance. Sometimes OID is unavoidable. This is especially the case in traumas and even some standard positions like sunrise knees. When you have a case where an absurd amount of OID is unavoidable, increasing SID will help decrease the magnification, as shown by Maddie G and Mr. Butterfly.
All right, party people, pretty much the gist of it is the longer the SID, the greater detail you're going to have in your image, and the less OID, the greater detail you're going to have in your image. So you want long SID, minimize OID, and you're going to have a great image. Right, Maddie?
Great image.
Okay, and that's about it. All right, smash that like button and subscribe. Smash that like button and subscribe.
We now know magnification is based on the distance from our X-ray source to our image receptor, as well as our distance from our object to our image receptor. Image distortion is unequal amounts of magnification to different portions of the same object. Some distortion is inherent to the image based on object shape and thickness, as well as the fact that our X-ray beam diverges as it leaves the X-ray source. The thicker portions of our object will therefore receive more magnification than the thinner areas. Distortion can further be influenced by alignment of our X-ray beam, our object, and our image receptor. If any of these are altered, the shape of our image will be changed. When distortion causes an image to look shorter than the actual object, it's known as foreshortening. When the opposite happens, it's known as elongation. This is what's known as shape distortion. Spatial distortion occurs when the previously discussed factors affect the spatial relationships between two objects on the image. In the image seen here, we would expect the right arm to superimpose over the left arm, but due to the increased object-to-image distance of the right arm, it would be more magnified and would appear larger on the final image. While some distortion is unavoidable, it's the radiographer's job to minimize the factors of distortion and create as accurate an image as possible.
We're going to talk about focal spot blur and the factors that affect it, SOD and OID. SOD here is the distance between my hand and the sun, which is our source. I'm changing the OID, object to image receptor's distance, by moving my hand away from the pavement. The outline of my shadow gets sharper the closer my hand is and gets blurrier the farther I move my hand away. This demonstrates that minimal OID results in a sharper shadow. Now I'm reducing my SOD by using a ceiling light. This time, changes in OID result in much more noticeable blur. The reason is that I've changed the ratio of SOD to OID. Outside, my SOD, the distance from the sun to my hand, was so big that changing my OID didn't make a drastic difference. My second SOD from the ceiling light is so much shorter that small changes in OID resulted in a lot more blur. A large SOD and minimal OID will produce the sharpest image. In an imaging department, this means that maximizing the distance between the X-ray tube and patient and minimizing the distance between the patient and image receptor plate will reduce focal spot blur. This is an important element of producing a clear, sharp radiographic image.
So this is the X-ray tube, and this is where the X-rays are made. This portion right here is the cathode. It is the negative part of the X-ray tube. On this side of the tube, this is the anode portion of the X-ray tube, and this is the positive portion of it. Now we will be talking about the anode field effect. The anode field effect is known as the intensity of X-ray beam that's greater on the cathode side than the anode side of the tube. So this side is going to be the anode side of the tube. It ranges from 6 to 20 degrees. So this side right here is going to be the cathode side. As you can see that there will be more X-ray photons and a higher intensity on the cathode side than the anode side. And that is what the anode Heal effect is. The X-ray intensity is weaker on the anode side because the X-ray photons lose some energy passing through the material of the anode itself. Knowing how the anode Heal effect relates to focal spot blur helps the tech position the patient in a way that produces the highest quality image possible.